What are the forces acting on this short track speed skater? Give me a force acting on him. Josh, give me one.
He has the force of like friction between the skates and the ice.
Um,
And his weight and normal force.
All right, let's focus on the weight. The idea of friction between the ice and the blade, you really want as little of that as possible. That's what ice skating is actually all about. We usually default and say, oh, it's friction, blah, blah, blah. But like when you think about it, friction doesn't play much of a role with these ice skates. That's the idea, would be to limit friction. But weight, obviously, right? What direction does the weight go, Josh?
It goes down.
Weight goes down. Now, what do you mean by normal force?
Well, the normal force will be going up because he has a point of contact with skates.
See, so the normal force, you think, does that?
Yeah.
It's also touching over. It's also touching over here.
Yeah.
That's kind of probably nice and small. Right? There's a problem a little bit with that normal force, right? Like the normal force of this thing is pushing upwards, right? And you know, I did tell you that the normal force pushes perpendicularly up from the surface, but like there's exceptions to every single rule, right? Like why is this normal force perpendicular to the surface? Because the bowling ball is pushing down on the surface perpendicular. All right, Sammy, what do you want to say?
Wouldn't the normal force go like at an angle from like where the angle that like the skate forms with the ice?
Yeah.
And that pushes. Wouldn't that be the normal?
Yeah. Like look at it. Why does the bowling ball even have a normal force acting on it? Because the bowling ball pushes down on the table, and the table pushes up on it. Is this person pushing down on the ground? Absolutely. Anybody ice skates, you dig your skates in. You're pushing down at this angle, which means the ground is exerting a normal force like that. Now, if the skater is skating in a circle, the circle would look like this, right? This is the center of the circle over here. Here's my center, someplace over here, right? The skater's skating like this. Is the weight in the radial plane? No. So is that a contributing factor to this circle motion? No. This normal force, is this in the radial plane? Nope, that's not a factor either. Is the other normal force in the radial plane? A component of it is, what's the job of F and Y? Is that in the radial plane? No. What's the job of F and Y? Well, F and Y here, or let's call this Fn2. What do Fny and Fn2 do? They support the person and counteract the weight. Otherwise, the person would be accelerating in the vertical plane. What's the job of the x component of the normal force? Carl. Perfect. This provides the centripetal force. So we're talking about this skater. If the skater's moving in a circle, the sum of the radial forces equals mv squared over r. What's the radial force? The x component of the normal force must provide enough force to keep this skater in the circle. What happened in that video that you watched at the start? What do short track speed skaters do all the time? They wipe out. Why do they wipe out? Because this is not big enough. Because what do? Like the whole idea of racing is to go really, really what? This they want really, really big. And the track has a very small R value. They need a lot of centripetal force, or they need a lot of force to keep them in the center of the circle. If this isn't big enough, what happens to them? They go where? They go straight and hit the outside padded walls. All right. So sometimes components come into play with respect to this stuff too. So there's all sorts of different situations that can happen here.